Welcome back, y'all. It's Professor Marinos. In this last lecture, we discussed how the negative charges in soil solids form the basis of electrostatic absorption of positively charged cations in soil, and how this forms a retention mechanism for these solutes. In this lecture, we're going to switch gears and talk about not electrostatic attractive forces, but actual bonds that form between minerals and organic matter in soil and different solutes. So not just electrostatic attractions such as ionic bonds, but legit covalent bonds, and how these form the basis of sorption of a bunch of different other kinds of elements.
So by the end of this video, you will be able to describe the chemical mechanisms by which both oxyanions and metalloid cations are complex to mineral surfaces and organic matter. And secondly, name two elements for which these mechanisms are important. And, I just gave you a pretty lengthy treatment of cation exchange capacity. I'm going to try and give this a somewhat lighter treatment, but hopefully just give you a taste of what is possible with specific adsorption. So let's get into that. So you saw this figure in the last presentation where we considered a goethite crystal, and this is the edge iron on this goethite crystal. So you have, repeating units of iron extending this way, but this is the one on the edge. And this is bonded to a hydroxyl group at the edge. And we discussed how this hydroxyl group, depending on the pH, can either lose a proton to gain a negative charge, or it can gain a proton so as to have a positive charge. So at high pHs, it gains a proton because there's an abundance of protons, and to move towards equilibrium, protons move out of solution. Whereas at high pH, there's a relative lack of protons, and so protons get kicked off of the edge of the crystal to cause a negative charge on the edge. And we thought about this kind of as acid-base chemistry, with these hydroxyl groups depending or behaving as kind of functional acid groups on the edge of this mineral crystal. But you can also kind of think about these as ligands. So these hydroxyls that we see here are just the same sort of hydroxyls that, for instance, can complex with aluminum. So we saw how aluminum complexes with between 1 and 4 hydroxyls, depending on the pH of the solution. And similarly, aluminum can also complex with these hydroxyls, forming an aluminum that's covalently bonded to this. Or another element that complexes can form a bond, such as chromium or cadmium. Any sort of element that complexes with OHs in solution will likely also complex with OHs on the surface groups of solids. And so we said in the previous lecture that complexation increases the solubility of a lot of elements. And that is true when those elements are being complexed with things that are in solution. But now you're looking at something that is attached to a solid surface. These hydroxyl groups are attached to a solid surface. And so if elements complex with these potential ligands, these hydroxyl ligands on these surfaces, what you'll see is actually things being removed from solution. So this is a mechanism of adsorption that can remove elements from solution via complexation. And these are inner sphere complexes, as we discussed previously. So this is what we mean by specific absorption. Specific absorption is ligand exchange. The mineral loses a hydroxyl ligand, where that ligand is replaced by another ligand that's complexing with it, such as, in this example, phosphate. You see these hydroxyl groups are on the edge, and you add some phosphates, and these hydroxyl groups are replaced by phosphate groups, PO4, and there's some protons added onto this too, which is also pH dependent. But so this is a ligand exchange mechanism by which this phosphorus is now covalently bonded to the whole mineral crystal via this oxygen, which is then connected to these irons. And indeed, if, say, an iron floated by and an iron complexed with this oxygen, we wouldn't actually say that this is a complexation reaction. We would say that this is just growth of the mineral crystal. This is like the nature by which atoms covalently bond to an existing mineral crystal and thus like expand the structure. But the fact that this is phosphate means that this phosphate can't further bond with more irons and oxygens. So this phosphate essentially terminates the iron crystal by sorbing to its side. But so this is the mechanism of specific absorption. by which an inner sphere complex is formed between, in this case, an oxyanion, phosphate, and a mineral surface via a covalent bond. And this is an equilibrium process, just like all other complexation reactions. And so it has various Kf values. And because clays can be complicated, and because organic matter, which this can also happen to, are very complicated, you might not have one single Kf value like we discussed for cation exchange. But you might have, a range of Kf values, but it can be pretty well defined. And these inner sphere complexes are a lot easier to nail down a narrow range of equilibrium values than, for instance, outer sphere complexes are. So it's an equilibrium process. You'll have equilibrium constants that govern the amount of potential sorbing ligand in solution versus sorbed ligand on the specific exchange complex. And so there is a general trend for how strongly these things sorb, or how large their equilibrium constants are. A larger equilibrium constant means that something is much more likely to sorb. And generally, this trend that you see is phosphate is one of the very, very strongest sorbing oxyanions through this ligand exchange mechanism. Sulfate is far weaker, but still can be appreciable in a lot of situations. Chloride is weaker still, and nitrate is even weaker, such that these really almost never form complexes with clay surfaces. Phosphate and sulfate do, though, and those are pretty important oxyanions that engage in ligand exchange and specific adsorption to mineral surfaces. So again, this is a complexation reaction. It's just that instead of something complexing with something in solution, it's complexing with a solid surface, thus removing it from solution. So I should also point out that multiple bonds are possible that can sorb things even more tightly. So here you have an arsenate ion. This is another oxyanion that forms complexes, fairly strong complexes. And you see here in this example, this arsenate is bonded to one oxygen on the surface of this iron oxyhydroxide crystal, or this might be goethite. But look over here. Here you have two oxygens bonding covalently with this arsenate. And this is called a bidentate complex. This is called a monodentate complex. Dentate means teeth or tooth. And so this is a one-tooth ligand, and this is a two-tooth ligand that, this is kind of a graphic metaphor, kind of like bites really strongly into this arsenate and bonds this very, very strongly. And so these monodentate adsorption mechanisms are weaker than these bidentate adsorption mechanisms. And things like phosphate very readily form bidentate sorptions or bidentate specific adsorption ligand exchange reactions. And so as a result, phosphate and arsenate and to a smaller extent sulfate are very tightly bound to soils to a large extent due to this bidentate adsorption mechanism. And just like complexation in aqueous solution, complexation between sorbents and sorbates are highly pH dependent. So you'll recall looking at this goethite that at a higher pH bears a negative charge on its surface. If you have a phosphate ion come by, that phosphate ion bears a negative charge as well. And so it would be strongly repelled by this negative charge that's on the surface of the crystal. And so it would really never have a chance to get close to engage in this ligand exchange mechanism. Contrast this with this goethite crystal down here at a low pH that's gained a proton, and the phosphate would be actively attracted to that edge of that goethite crystal because the positive charge of the goethite crystal is attracting the negative charge of the phosphate group. And so you'd be very, very likely to exchange a phosphate with this OH2 group here at a lower pH. And when you have neutral groups, such as this OH here and this OH here, that's when you generally see intermediate grades of specific adsorption. you're not necessarily drawing all the phosphates close enough that they can very, very readily exchange with the surface and form a complex, but you're also not repelling them either. And so this mechanism is why you have major phosphorus fertility issues in the tropics, and why, for instance, lots of tropical rainforests, their growth is thought to be limited by the availability of phosphorus. You have this iron that exists um, in these forests, in these iron oxyhydroxides that are at low pH. They're very acid weathered soils, and they all have positive charges. So any phosphorus that becomes available in the soil almost immediately becomes occluded, becomes attached to this iron, and becomes not bioavailable for plants. So phosphorus sorption, particularly in highly weathered soils, in the tropics, this is also a huge deal in the southeastern United States with agricultural soils. Um, they tend to be very, very phosphorus poor. And you can add phosphorus fertilizer, and nothing changes because the soils basically have an unlimited capacity to sponge phosphorus due to this ligand exchange specific adsorption mechanism. So we've said that specific adsorption is dependent on clays being in soils. And just to kind of hammer this home, this is a nice sorption isotherm with a soil that is at 8% clay. And you can see that it sorbs vastly less phosphorus per amount of phosphorus in solution compared to the soil with 10% clay, which sorbs phosphorus a lot more tightly. And so, sandy soils tend to be less retentive of phosphorus and can have higher phosphorus fertility, whereas clay soils can very tightly bind that phosphorus, and it takes a lot of effort by plants secreting enzymes and such to liberate that phosphorus from the clay complex. So it's not just oxyanions that will do this, things like phosphate and sulfate and arsenate. Also, different transition metals would do this exact same process. Any metal that will form a complex in aqueous solution, here we have the example of cobalt, will also form complexes on the surface of minerals. And so here you have a cobalt that has a bidentate complex with aluminum shown here, and I guess also a bidentate complex here with aluminum. This black dot is supposed to be aluminum, and there should be protons on this typically, but this figure just doesn't show them. Um, so yeah, the general rule of thumb is if something will complex in the water with various ions, particularly hydroxyls, because that's what's on the edge of these clay crystals, then it's also very likely to complex with mineral surfaces. But it has the opposite effect. Complexing with things in solution raises their solubility, whereas complexing with things in solid phase reduces the solubility of a particular element, as you might guess. And some metals do complex, some metals don't complex. Let's consider the ones that don't complex. For instance, a good example of this are your alkali metals and your alkali earth metals. Take potassium and sodium. Those don't really form complexes. They are so electronegative that they they're so weakly electronegative that they almost never share electrons. They almost never form covalent bonds. They're almost always forming ionic bonds. So if you have metals like this in the inner sphere that are forming what we would call an inner sphere complex, actually this is just mostly electrostatic attraction. This potassium will never ever want to share an electron with the oxygen because it has, if it loses an electron, it has a full valence shell, and so this is a very stable electron configuration for it. So this is an inner sphere complex, but this is pretty much only driven by electrostatic attraction, whereas this is true covalent bonds forming between a metal and an oxygen ligand and another metal. So you have basically what you have is various degrees of bonding. Covalent versus ionic bonds are never like a true dichotomy. It's always existing on a range between a fully ionic bond and a fully covalent bond. And what you see here is the same thing. Depending on the electronegativity of the elements in question that are forming inner sphere complexes, you'll have a range of either covalent ligand exchange mechanisms or strictly electrostatic attraction mechanisms that's strictly driven, again, by the electronegativity of what could potentially be bonding to the surface. So just to summarize this point, Metals and metalloids that are moderately electronegative will form covalent surface complexes, whereas very weakly electronegative elements will simply sorb to the surface via a strong electrostatic attraction. Again, this is a strong attraction because it's an inner sphere complex, and so these ions have a very, very high charge density because there's not water surrounding them to dilute their charge density. So it is still a strong ionic bond with the surface, but it's really not nearly as strong as a true covalent bond between with electron sharing between oxygens.
Okay, so that's all I have for you right now. Next week, we're going to launch into one of my very favorite topics, redox chemistry, so I can't wait to see you then.